Chemical equilibrium. What is a chemical equilibrium? It's a reaction that is reversible, meaning it goes both forwards and backwards. And it will at some point reach a point where the forward reaction rate is equal to the backward reaction rate, meaning that product is being broken down at the same time it's being produced. So from a macroscopic level, we will not be able to see any changes, and it would seem that the reaction is not taking place at all, but it surely is. So if you look at the example from our experiment, the reaction is iron-free ions colliding and reacting with thiocyanate ions to form iron thiocyanate ions. But the reaction is reversible, meaning that it also goes the other way. So the iron-free thiocyanate would also decompose into its components. So we can use the equilibrium expressions as a mathematical way of explaining how this happens. So the equilibrium expressions is defined as the equilibrium constant, capital K, equal to the concentration of products over concentration of reactants, which in our case is the concentration of iron thiocyanate over the concentration of iron times the concentration of thiocyanate. Now I know that you usually put the iron symbols on top, but it would not allow me to do this, so we forget it. But when there are more reactants or products reacting or being formed, we put a multiply sign, we multiply the concentrations. And we take them to the power of their coefficients. But as we can see here, in all three cases, they have the coefficient 1. And when we take them to the power of 1, we do not be able to see this. And it's important to note that at equilibrium, the constant is equal to Q. And Q is this here, the fraction. And Q can change when we put stress upon the system. So factors and requirements. It has to be a reversible reaction, or else it will not take place. And it also has to be a closed system, because in an open system, particles will just disappear. As we can see here, when water evaporates, it will just disappear into the atmosphere. But in a closed system, water would evaporate but still be in the system, and it will then condense into the same system. And because of this, at some point, the reaction would, it's not a reaction, it's a physical change. So at some point, it would evaporate and condense at the same time, only because it's a closed system. So how do catalysts affect the chemical equilibrium? They do not directly shift the position of equilibrium, but it makes the whole reaction take place faster, because it speeds up each reaction at the same rate. So the forward reaction and the backwards reaction are sped up equally. But this can be used in industries like the production of ammonia, because when they both sped up, it would reach the position of equilibrium faster, which is very useful. The position of equilibrium can be shifted if a stress is put upon a system. At equilibrium, there are different ways to explain why it tries to reach the point of equilibrium. The first one was the equilibrium expression. If we look at the expression here, we can see that if we increase the concentration of iron, which is one of the reactants, we divide by a larger number, and Q becomes smaller than K at that moment. It would then try to fix itself by making Q equal to K again. So it would break down products into its reactants, which would give a higher number, and at some point it will be at equilibrium again. Another way to explain this is the rate expression. The rate expression is defined as the rate is equal to the constant times the concentration of a reactant times the concentration of another reactant. So we know that if we add iron-free ions, the reaction going towards the right will be faster than the one towards the left, according to this expression, because it will be a larger number. So when this happens, this means that it will be forming products faster than products decomposed. So overall, the concentration of products would rise because of this. But at some point, the rates will even out and become equal again. And we can also use Le Chatelier's principle, which states that if a stress is put upon a system, it will shift to doing the opposite. So in our case, we added iron-free ions to the system, and we do the opposite, which is to decrease the concentration of iron-free ions, and this does this by producing more products which uses up its reactants. The concentration of reactants would go down, the concentration of products would go up. Yeah, so the experiment was to show how different factors would change or shift the position of equilibrium. And it's important to note that the product being formed is red, which you can see in these pictures. The picture of the left is where we poured our solutions. We started with putting the reactants, there were no products. We put iron-free ions and thiocyanate in the same solution, and they would quickly reach the point of equilibrium. If we look at the graph, we can see how it happens. So we add only our reactants, so they decrease, the concentration decreases while it's forming the product, and they decrease at the same rate because they have the same coefficient, so they've been used up 1-to-1. So they decrease, and at the same time the product's been formed, and at some point right here they reach the point of equilibrium where the rates are equal to each other, so the concentrations do not change. And on the picture on the left is where we have just poured our reactants into it and made it reach equilibrium. And on the picture to the right is where we have put different kind of stresses on the system, and on a microscopic level we can see the differences here, which we'll go into now. Test tube 1. In test tube 1 we added solid iron nitrate. So the stress here is adding more iron-free ions. So it tries to, this reaction now shifts to the right to decrease the concentration of iron-free ions that we just increased. So it will produce more product, the red product, and to decrease the concentration of iron-free ions. So if you look at the picture, you can see that it becomes a darker red because more of the red product has been formed. And we can explain this at what's it called, expression here by looking at it. If we can see that a Q becomes a smaller value because we divide by a greater number at that minute, only at that minute, and then it reaches equilibrium again where Q is equal to K. Test tube 3. Actually test tube 2. So we added solid potassium thiocyanate, where the stress here was thiocyanate, which then again produces more of the red product and giving us a redder solution compared to a tube of reference here, which is the normal light one. And this is because it would then decrease thiocyanate again and iron to form more product, and Q here is still smaller than K. Test tube 3 is the addition of ascorbic acid, which reduces iron-free ions to iron-2 ions, a reduction. So here the stress is removing iron-free ions from the solution. So this will shift towards the left, which is to increase more iron-free ion, to concentration of iron-free ions. So the red product is being broken down into its colors components. So on a microscopic level, it loses its red color and is almost colorless. Here Q, at that moment, Q is greater than K because we divide by a lesser number, a lower number, which then gives a larger number in general. Test tube 4, we added silver nitrate, and here the stress was removing thiocyanate because the silver nitrate would react and form a precipitate with thiocyanate called silver thiocyanate. So we'll do the same, it would shift towards the left to produce more thiocyanate, so the red product was being broken down. And on a microscopic level, we can see that it still has a color, but it's a lighter color than the red on the right on the tube for the tube of reference. Here again, Q is lesser than K because we divide by, it's bigger than K because we divide by a lesser number. Test tube 5 and 6, we added heat and cold. If we look at our test tube 5, you can see there's a lighter color than our tube of reference here. And we now know that this means the product has been broken down. Since we've warmed up the tube, we can now know that it's endothermic because according to Le Chatelier's principle, it would do the opposite of what the stress was. So the stress was heating, so the system would try to decrease the heat by favoring the endothermic reaction, which is the reaction towards the left. So the red product has been broken down, which gives us a lesser red color. For our tube tube 6, it has a darker red, if you can see this here, than our tube of reference. And here we decreased the temperature, so it favored the exothermic reaction, which was towards the right, forming more product, making it darker red. And in this case, our Q value does not change. It's our K value, which is equal to our rate constants divided by each other. And our rate constants are, they're changed by temperature, they're affected by temperature. And the last test was the addition of water. In this case, we diluted our solutions by diluting it half, so the concentrate was half. Before we diluted, it was 1 to 1 to 1. Then we diluted the concentrations by half, so it was half, half, and half. But summing it up, it would be 1/4 on the reactant side and a half on the product side. So we would have less reactants, and the equilibrium would shift towards the left to form more reactants. So it would lose its red color since the red product has been broken down again. So they will be equal to each other again. So here we see that it's lighter than a tube of reference. But looking from the top, it should have the same color, since we see all the same. It's the same amount of particles in each tube, but it just has different concentrations. So looking from the top, it should have the same color, but we do not see this in this case. So to sum it up, chemical equilibrium is a system that can fix itself when a stress is put upon it.